Okay, this is the name of the experiment, that is Stefan Boltzman constant apparatus. Aim to determine the Stefan Boltzman constant. Specification: mass of disc, that is small m, is equal to 4 grams, that is 0.004 kg. The diameter of the disc is, that is small d, is equal to 15 mm. Then specific heat of the given specimen is 410 joules per kg degree Celsius. If I want to determine the Stefan Boltzman constant, I need to use radiation heat transfer equation. What is that? Q is equal to sigma A into Th raised to 4 minus Tc raised to 4, where Q is equal to rate of heat transfer, sigma is the Stefan Boltzman constant, then A represents area of the specimen. Okay, then Th is the hot body temperature and Tc represents cold body temperature. These are some radiation examples. Okay, this is our experimental setup what we have in our laboratory. Initially you have to, so now I will tell the parts of the experimental setup. One is heater. Okay, second one is the, first one is the power switch, second one is the heater, then is the temperature indicator, hot water chamber, hot water tank, heater, sixth the filter, then seventh is the hemispherical enclosure here, eighth is the test specimen, and ninth is the water drain. This is what parts of the experimental setup. Now how to conduct the experiment. Okay, here you can see here now, this is schematic view of this particular experimental setup. Now you have to switch on the console button, then you have to switch on the heater, then you have to set the temperature of heater as you want. That is, generally we will set it as 80 to 90 degree Celsius. That means when you set it 80 to 90 degree Celsius, this heater is placed here, right? There is a water tank. It consists of 75% of water here, right? When you are switched on the heater, then you have set it for 80 degrees Celsius for using a thermostat, right? So then water will get heated up to 80 degrees Celsius. Then it becomes hot water. Then you can see here now, then that hot water we will pass to the hemispherical enclosure here now. So then after that, when you pass the hot water into the hemispherical enclosure, then you have to wait for at least 10 minutes. Then what happens? This water will transfer heat to the hemispherical surface here now. Again it is a metal. Then it is completely closed. You have to keep it in mind. Then what happens? After 10 minutes, heat is transferred to this hemispherical enclosure. Then it is going to attain steady state. That temperature we will call it as a enclosure temperature. Now by this now you can see in this knob, the T1, that knob is set to the T1. That indicates, T1 indicates what here? Temperature of hemispherical enclosure, that is TE. That you have to write it here now. Our enclosure temperature what we got, that is 79.3 degrees Celsius. Convert that into 352.3 Kelvin. Okay, after this what you have to do? You have to rotate this knob and you have to set it to the point number second temperature reading, that is 0.2. Okay, then you have to at 0 degrees Celsius. At that moment immediately you have to take the test specimen reading, that is T2, right? T2 represents test specimen reading. Where is the test specimen? Here you can see here now. When what happens? It is already gets heated, right? That heat will transfer from here, this surface to this surface without any media. So that is radiation heat transfer, right? At 0 degrees, at 0 second, how much temperature it's attained? That you have to take. T2 is equal to, you can see here now, at test specimen's temperature at 0 second is 33.1 degrees Celsius. Then again I will leave it for 5 seconds. Then you take the test specimen reading. Then I will get it here at 5. After 5 seconds I got the test specimen reading as 39.1. Then you have to take the reading like that in the interval of 5 seconds. Then like that you have to take readings for at least 1 to 2 minutes. So after 5 minutes, at 10 seconds, the temperature of the test specimen, after 10 seconds, temperature of the test specimen is increased to 39.5. At 15, it is 39.5 again. 20, it is 39.5. 25, it is 39.7. Like that, you have to note down the reading. I have started with 0 seconds. Then I reached to 125 seconds. At 125 seconds, the temperature of the test specimen increased to 44.9 degrees Celsius from 33.1 degree Celsius. Almost 10 degrees Celsius temperature is increased. That means what? The heat is transferred from this surface to test specimen, that is around temperature of what? 10 degree. Isn't it? That means heat is transferred without any media. There is that is radiation heat transfer. Okay. After this value, what you have to do? See here now. Separately I have written Ts is initial temperature of the specimen. Initial temperature of the specimen initially means what? At 0 second. That is 33.1 degree Celsius. Then convert it into Kelvin. It becomes 306.1. After getting this value, after getting these readings, you have to do the calculations. So first calculation, that is a slope. You have to draw. What is the slope now? In vertical component, you have to take the temperature. In horizontal component, you have to take the time. Okay. So at 0 second, what is the temperature? That is 33.1 degree Celsius. At 0 point, temperature is 33.1 degree Celsius. Similarly, at 5 seconds, that is 39.1. At 5 seconds, 39 point, like that you have to mark all the points from 0 to 125 second. Okay. So now you got this curve. After this, what you have to do? You have to take any 2 points, draw one vertical line and draw one horizontal line here now. When you draw one vertical line, you will get the temperature difference. You just measure here in vertical component, you will get the temperature, change in temperature. That is temperature difference that you have to note down. Okay. Similarly, you draw you can measure this dt, that is in x direction, that is you will get the distance. Okay. That distance is nothing but not actually distance here. The distance indicates time actually. Okay. Here from my readings I got change in temperature as 0.25 degree Celsius. Then change in time is 6 seconds. Then I will divide 0.25 divided by 6. I will get 0.04 degree Celsius per second. It is a degree Celsius and it is second. It becomes degree Celsius per second. This is my dt by dt value. So after this, you have to calculate the surface area of the test specimen. As I told you, the diameter of the test specimen is 15, right? So now to calculate the surface area of the test specimen is, we have the formula. What is that? AD is equal to 5 by 4 into d square. So now we have to substitute the value. 5 by 4 into d square is nothing but what? 15 into, because 15 mm they have given, you have to convert that test diameter into meter. That is 15 into 10 to the power of minus 3 whole square. Then you will get the area of the test specimen as 1.767 into 10 to the power of minus 4 meter square. Okay. Next, what you have to do? You have to calculate the Stefan-Boltzman constant. Our aim is to calculate the Stefan-Boltzman constant. What is the formula? We have this formula. That is Stefan-Boltzman, that is sigma is equal to mCp into dt by dt divided by AD into T raised to 4 minus Ts raised to 4. Okay. Now, where T represents enclosure temperature, that you have already written here, that is 79.3 degrees Celsius. They have converted. The enclosure temperature is 352.3 Kelvin. Next, minus Ts, right? Minus Ts is nothing but what? Test specimen initial temperature. That is nothing but what? 33.1 degrees Celsius. That you have converted in as in Kelvin. That is 306.1 Kelvin. Okay. So now I have substituted here now. So now substitute T, you know T, you know Ts, substitute, you will get the sigma. Now what I will do? I will substitute mass is equal to 0.004 into specific heat of the test specimen. That also already is given in the specifications itself now. Here Cp is equal to 410. That same thing I will substitute here now. So then what happens? 410 Cp. Then dt by dt is, I got it here 0.04. Then divided by AD is already calculated. That is 1.76 into 10 to the power of minus 4. Next, T is into bracket, T is 352.3. Okay, then Ts is 306 here now. Then I have substituted here. Then I will get sigma is equal to 5.83 into 10 to the power of minus 8. That is our result actually. So that is our result. Then final result will be Stefan-Boltzman constant from our experiment. We got it as 5.83 into 10 to the power of minus 8 watt per meter Kelvin to the power of 4.